All right, so let's talk about balanced three-phase voltages. That's really when three-phase is interesting. When my three phases are equal in voltage, equal in frequency, and they just have this 120-degree difference. So this has to begin with the generator. Right? Our electric generator has to create this power with three different phases. So we talked a little bit last week about a motor, right? And a little bit about how a motor actually works, how it's generating the magnetic fields. And now we need to talk about not the motor, but the generator side. So what happens if I turn a motor and I suck current out? That's a generator. It's the same basic physical configuration, right? So last time we were talking about motors, I showed essentially a single phase motor, right? But in the case of a three-phase generator, we have a rotating magnet, and you're rotating that magnet with whatever your power supply is, right? If you're burning coal or natural gas, or if you're turning it because of a dam, right? And the hydroelectric power that's being generated, if you haven't torn your dam down, right? If it's still working, then you have some mechanical force that's turning the rotor in the middle. And the stators are the electric coils around the outside. So now if I have this magnet in the center, right, again, it has a north-south pole, each of these stator coils, you can see the way, it seems a little strange maybe the way it's drawn, but the stator coil, for example, here it shows A prime. What that is that's a coil of wire that comes out of the board and goes back in at A prime, right? And then goes in and comes back out. So this is a single loop of, well, many loops of wire wrapped in that direction, right? And so that generates, or that it may be a split coil, it may not be a single big wrapping, but anyways, it's a coil of wire that generates an electric field in this direction. You remember in physics when you learned about magnetic fields, you had to do the right-hand rule. So if the current were flowing out of A into A prime, it's going around like this. Right-hand rule says magnetic field points in this direction. Right? And so my north-south magnet wants to rotate to align with that magnetic field. But then I have another pole. Well, in this case, it's a generator. Right? I rotate that that permanent magnet, and it creates that magnetic field in that direction, which causes current to flow in that loop of wire in the stator. But then as it's rotating, there's not just the AA prime, there's also this BB prime, another stator coil. And it's not quite aligned in the stator coil. But as it rotates, it starts to build the voltage. It starts to cause current to flow in that second stator coil, the BB prime, right? But of course, as it does that, as it moves to align, well, in this case, they're showing the arrow rotating this way. After A, it would align with C, and then it would align with B. But at any rate, as it aligns with the new set of coils, that coil has a peak in its output. But now it's not aligned with A. Right? So A is falling off. So as the A coil drops, the B coil is rising, and then of course it continues to turn, and it turns and it starts to align with the C coil. That C state, right? Which starts to bring a rise in the current flowing or a rise in the voltage generated in the C coil as the B continues to fall off. But now it's moving toward realignment with A, right? So you see that each of these three coils, the stators, generates its own voltage. It acts like a voltage supply, each one independently, even though it's inside of one generator, right? One physical generator. So we get three separate voltages out, but they happen to come out 120 degrees out of phase with each other. So the 120 degrees is literally related to the physical arrangement of the stator coils being turned 120 degrees relative to each other. So you could generate a a six-phase generator. And they do that sometimes, right? And they'll have a many phase generator, and all they have to do is they add more windings. Yeah? Not necessarily, except for that in fitting all of those coils in, they may not, depending on the size they wanted to use and how much force they have available, right? That would all depend on the physical arrangement of the actual motor. Yeah. So if they could still fit in another set of wires and it would physically fit, because again, you're winding wires, it does take some space to do that, then they could get all three to come out, or all six to come out the same. Right? They might have to push the magnet harder, because of course it's losing energy, just like the argument we made the last time that if you put current in and it's trying to force something to turn, it uses its energy overcoming that friction in the rotation. The same thing's happening now in that you have to push harder if you're sucking energy out as current. You have to push the permanent magnet in the rotor harder to get it to do that. Right? So like if I run my little gas-powered generator at home, when there's nothing connected to it, it doesn't hardly, it burns very little gasoline, because the gasoline motor doesn't have to work very hard to turn the generator. But as I start to draw current out, you can think about, again, by drawing current out, I'm trying to change the magnetic field, and so I'm going to suck energy out of the magnetic field, which makes it harder to turn the rotor. And so the gas motor has to work harder to keep that rotor turning. So again, if I have multiple phases, I might have to push the rotor harder, use more gas, more water flow, or whatever. Okay? So that's in a very, very simple picture, but that's where it's coming from. And so it's not very complicated. Most of the generators, if you've taken the opportunity, did anybody take the opportunity to go tour the natural gas power plant in the fall? ASME put on, the mechanical engineers organized a trip to the power plant. But when you go to the power plant, they have a big turbine that burns natural gas, and as that thing spins, it generates three-phase power, because the turbine spins, and it spins a big generator attached to the end that has these windings. So we can assume it's not that hard to get out a three-phase signal. Right? Did you have a question, Lewis?
Yeah. Will we only find these generators at power plants?
No. You could make one. You could have one. Again, it's just that most of the time, it is more expensive. So most of like the small generators, like your little small gasoline powered generators, a home utility generator, they're not designed to generate three-phase because your home doesn't use three-phase, right? But you could get one, yes. Where if you knew you needed to power some three-phase equipment, yeah. But again, it's typically then, of course, a generator is designed to sort of replace power distribution. So if you're off in some isolated area and you want to create like a small grid to run like a camp or something like that, or to run a mining operation or something, you may very well use three-phase generators. Because again, the other advantages, saving money on the wires that have to run everywhere, distributing power more evenly, all those advantages still apply to you. And this would run more efficiently given whatever your fuel or your motor force is. But you're not likely to buy one for your house. Right. So we can see that we can generate these balanced three-phase outputs. Right? So we're going to use our favorite Y delta. Right? It really wasn't useless. Right? When we learned about Y delta, it was preparing you for three-phase, right? So there are two possible configurations. Our voltage supplies, those stator wires, come out, give us a voltage, and they could be configured, as I mentioned, in a Y configuration, where all of the negative terminals are attached to a single point, and that provides us a neutral connection. Right? Or they could be arranged in a delta configuration, where they're arranged kind of head to tail. Right? The negative supply of one of those voltages is attached to the positive terminal of the other voltage supply around the triangle. And so we're going to see how these different balanced configurations.
Is that side back to neutral?
Well, it doesn't need a neutral, no, because again, voltage is always measured relative. And so you just measure the voltage across each one of those, and you know that whatever voltage this is generating will appear between, in this case, the voltage at A and B appears between A and B, right? But you're right, it doesn't provide a neutral. So you don't have that advantage, which you may want. So if you do want the neutral, you need to make sure that you're using a Y configuration. And again, though, there are differences, benefits, to the various configurations. In the case of this neutral, right, if you were measuring the voltage between the A point and the neutral, you're going to get whatever that leg is providing. We're going to define these with some terminology in a minute. But then if you're between the A and the B, you're going to have a different voltage coming out, right? And so we'll see how that works as well. Yeah?
I'm not sure what's the difference between a neutral and a ground.
Well, a neutral is a common point. It becomes a ground if you ground it. So neutral doesn't necessarily mean that you're tied to the ground. Last semester, you guys in the lab, you had one lab on power distribution, right? With those yellow boards, the Hubble boards, right? So when you were doing that wiring, you saw that most of those were all, of course, single phase, but most of those cables you were running had 3 wires in them. They had a hot, a neutral, and a ground. And so in those cases, the current is expected to flow out of the hot terminal and back through the neutral line, right? Ultimately, at the power distribution box, the neutral is typically attached to the ground, right? And so ultimately, yeah, that is ground, and that's why, though, you run a separate ground wire just as security. It's a backup. So you don't have to have that third ground wire, which is the third small plug, the small inlet on your receptacles. But it's an extra safety precaution, because what if that neutral wire went bad? There would be no return path, right? Or what if you were touching ground, like standing in a puddle, for example, right? And if you were touching ground, you now become an easier path back to ground than going through all of that wire back to the distribution panel. And so having an additional ground wire can help alleviate problems, right? It's a safety precaution. But ultimately, usually, the neutral wire is, in fact, tied to ground. And we'll see that in a lot of our problems when we deal with the 3-phase systems. Most of the time, we're going to see that they attach the neutral to ground. But they don't have to. Ground is literally just that. If you look at the ground connection at your home, there is a big rod of metal hammered into the earth outside of your house. And it goes down 6 feet, whatever, 5 to 6 feet, ideally, at least 3 feet usually. And they just hammer it into the ground, and then they attach a big wire to it. And so it's actually attaching your house electrically to the earth, to the ground around you. And that's where all of the extra electrons go, right? If they have nowhere else to go, they go back down and just get distributed in the earth, right? So the moisture in the ground, the minerals, the salts, and things like that, all inside of the ground, they will conduct electricity. And so it carries away all that extra charge. That's why lightning strikes, because the ground is the reference potential for everything that we do. Yeah?
I don't know. Is it possible to recycle that energy?
To recycle it? Well, while there's current flowing into it, right? In order to get power, which would allow you to do work, you have to have voltage, right? Well, ground is 0 volts, right? So that's where everything goes when it's done doing work. Until it gets there, yeah, right? You're using it all along. But that's because you've already raised its potential somehow, right? In the case of a lightning strike, the potential has been raised by the wind blowing, clouds and moisture through the atmosphere and sucking electrons, right? Separating electrons off. That mechanical work that's done because of the sun hitting us and heating the air and causing clouds to move, right? So, builds up a big voltage, a big potential. And then they want to not be a big potential anymore, so boom, lightning strikes, and those electrons all flow back down to ground. All that energy is released, right? We forcibly separate electrons from where they want to be so that we create a potential, either in a battery or with a generator. And then we use all of that energy up every time by the time it reaches ground. That's what KVL is. Right? KVL is telling us if I started at ground and then somehow I managed to raise the potential with a battery or a generator or whatever, then I get to use all of that energy, but just until I get back down to ground. When I get back down to ground, I have to be back to zero, right? And all the energy is gone. So we are, in essence, recycling that energy all the time. Once those electrons are back in the Earth, they become available to use again, if you will, by somehow separating them and increasing their potential again, which we have to figure out where does that energy come from to be able to do that, right? And again, maybe it's the sun, right? If we have a solar panel, the sun hits the solar panel and it separates those charges. Those charges then flow through the wiring in your house, back to ground, and then when the sun hits again, the solar panel is able to pull an electron from the ground and separate it and give it some extra energy thanks to the sunlight hitting it, and then it's able to be used again to do work for you. So all of that energy, of course, those coming from the sun. Maybe it's coming from the fuel you burn or whatever, right? So yeah, so the electrons are never gone, they're just moving around. So when we talk about the balanced three-phase voltages, we describe them with some terminology, and I apologize if I get a little confused because again, the terminology gets used in several different configurations. So the balanced phase voltages, right, which is the voltage on each one of those legs, are equal in magnitude, but out of phase with each other by 120 degrees. So that each of the individual legs is what we know as a phase, because we're looking at the phase difference between them. The phase sequence is just the time order in which each of those voltages goes through its maximum. So again, when we showed the first slide here, right? What order in time do the three voltages reach their peak? And in this case, right, we see A, then B, then C reach its peak. So that just tells us the order, and it's based upon the direction of rotation. Yeah. So like if you look at the North Pole on this magnet, if it were aligned, well, even right now, right, its configuration now, it's coming into alignment with A. It's going to be pointing this way. The next one it aligns with, then, hang on, gotta look at this the right direction. These are the primes. So if we are, all right, so let's say we follow the South Pole. South Pole is to the right of A, and then it moves, and the next pole it passes is to the right of the B, and then it rotates around and it passes the C. So it's going A, B, C, right? In that order. That helps us to remember, based on the direction of rotation of the motor, of the generator, what direction is our generator running. If our generator suddenly started turning the other direction, the phases would come out in the opposite sequence. That's really useful to remember because when you wire up a motor, if you wire up a three-phase motor, the sneaky thing about a three-phase motor is you don't know which way it's wired up. So you don't know when you get your two hot phases that you come out and you wire it up, you don't know which one is, you've got three wires coming in, and when you wire them up, based on the phases coming out, it will push the rotor in one direction. And that might be the wrong direction, right? So you always test a three-phase motor for its direction of rotation. You turn it on, it rotates, and you look at it physically. Which way is it rotating? Is that the right way? If it's not, you take any two of those wires and you swap them. And then it will run in the opposite direction because it changes the phase sequence. Right? So that's tuck that one away in the back of your head for the day you have to attach a three-phase motor to something, because you definitely need to remember that one. There's always an arrow, or there's like an arrow if there's a pump, for example. Most of the time that I've used three-phase motors, they're running like vacuum pumps or big water pumps because you need a lot of power. And so in those cases, the motor can run both directions, but if you turn the pump around the other direction, you start shooting water the wrong way. Most people don't like that. You know, they're not usually happy if the water starts shooting out when they were expecting it to get sucked in, or vice versa. Yeah, and you have check valves that cause you trouble. So those things usually require a particular rotation. So just watch for those. And that's because of that phase sequence. No one way is better than the other, right? Because they're all equivalent. It's just we do want to know which order they're in. So it will describe it as being an ABC sequence or an ACB sequence, and right, you'll be able to determine that. Also, when we describe something as a balanced load, it also means that the phase impedances are equal in magnitude and in phase. So the load that we attach to each of our three supplies should be equivalent for our system to be considered a balanced load, or a balanced system. Okay? So we have balanced phase voltages. That's when we look at the supply side. And if all three of the supplies are equal in magnitude, and they're only different in phase, then it's a balanced voltage. If we look at the load side, the thing we've attached, right, the impedances we've attached, it's a balanced load when each of those are equal in both magnitude and phase. Okay. So, again, quick example to talk about phase sequence. So if I have a set of voltages, VAN, VBN, VCN, what is the phase sequence? Right. So they all have the same magnitude, 200 volts.